Okay, here's an example of a distance rate time problem. And I picked this one just because we can get at it two different ways. One, we can do it a traditional way using systems of equations. And we can also get at it just by thinking about the reality of the situation and doing some simple arithmetic. So the first thing I'm going to do here is I'm going to draw a picture of the situation. So I have a river that's going downstream, and I have a boat, and it goes downstream 45 miles, okay, in 3 hours. On the return trip, I guess it's just turned into a submarine. On the return trip, it's coming back upstream. It has to go that same 45 miles, only this time it does it in 5 hours. The current's working against it, whereas going downstream, the current was working with it. Well, right away when I looked at my picture and started thinking about this, I said, okay, let's go to just the straight problem solving way first, just thinking about it logically. I know downstream I'm going 45 miles in 3 hours, which gives me 15 miles per hour. So I know that this is the speed of my boat, which I'll call R, plus the current. Going upstream, I know that I have gone 45 miles in 5 hours, okay, and that gives me 9 miles per hour. In this case, it's the rate minus the current. Well, the pretty easy way to figure this out is to take the average of the two, because that's going to be the speed of my boat in still water, because that's going to average out the speed of the current. So if I take 15 plus 9 and divide it by 2, I will get 24 divided by 2, which gives me 12 miles per hour, which is the speed of my boat in still water, which means 3 miles per hour must be the speed of my current. Okay, so that's one way I could tackle it, just by thinking about the reality of the situation and doing a little bit of arithmetic. Now, of course, since we do deal with math classes where people want to see equations, we can do this with equations using the same idea. R is the speed of the boat in still water, and C is the speed of the current. And I know that that is the total speed of the boat going downstream. So this is my speed, total speed. And I know that my speed, or my rate, times time, which is 3 hours, is going to be equal to distance, which is 45 miles. Okay, so here's my time, and here's my distance. Likewise, I have another equation that uses almost the exact same numbers, the exact same idea for sure. So this is my speed upstream, which is going to be times 5 hours to get upstream, is still equal to the same 45 miles. So this is my upstream, this is my downstream equation, and this is my upstream equation. Okay. Well, if I take both of these equations and expand them out, I will get 3r plus 3c is equal to 45, and I will get 5r minus 5c is equal to 45. Obviously the first one has a factor of 3, so I'm going to divide that out and get r plus c is equal to 15, and the second one I will factor out of 5 and get r minus c equals 9. And now we can see with both variables on the left side of the equation, this is absolutely perfectly set up for either the elimination method or its close kissing cousin, probably more like a brother, matrices. So if you're going to put this in your calculator as a matrix, it would go in as 1, 1, 15, 1, negative 1, 9, and then of course you would use everybody's favorite RREF, row reduced echelon form function, with that particular matrix. And that would give us the solution. We're going to go ahead and do this algebraically with elimination. So remember from the introduction to solving multiple equations that equals added to equals are equal. So if I add straight down, I get 2r is equal to 24, r equals 12, just like I found up above. Now remember my advice in previous problems. When I want to find c, I'm going to go ahead and substitute back in both of these equations at this independently of one another, just to make sure I come up with the same value of c. It's just a way to check what's happened here. So I'm going to take 12 plus c, because that's my r, that's my rate of my boat, still water, times 3 is equal to 45. That will give me 36 plus 3c is equal to 45. So 3c is equal to 9, which makes c equal to 3. Okay. If I try that in the other equation, 12 minus c times 5 is equal to 45. That will give me 60 minus 5c is equal to 45, which means that negative 5c is equal to negative 15, and c again is equal to 3 miles per hour. So I've done the check on myself to make sure that this works in both cases. As before on other problems, as I mentioned, don't just leave your answers like this. They're just kind of out there floating, and we instructors have to go looking for them, and the more we look, the less we want to give you credit for anything. So I'm going to close off the problem here by just adding a little statement at the bottom that says the speed of the boat in still water is 12 miles per hour and the speed of the current is 3 miles per hour. Okay. Notice this also does fit within the domain that we know that this problem needs. Obviously, for a case such as this, for my domain, just to look at the reality of the problem, I know the speed of my boat has to be greater than the current. How do I know this? Well, think about going back upstream. If your boat goes slower than the current, then the current is going to have the bigger effect, and it's going to wash your boat downstream, albeit at a slower pace, but it's still going to go downstream. And as I look at my answers, I do see that indeed R is greater than C. We'll do one more problem like this that involves a little more work and is a little more complex, but I did want you to see a problem like this one that sometimes can be solved in a more obvious manner than tackling it directly with algebra.